So let's go ahead and try a third-class lever example. And you might notice that I actually gave you a picture of a third-class lever. And this is because at the end of this, you might wonder what's the point of a third-class lever. You might think it's a bad idea. But this is sort of a practical example of a third-class lever working very, very well and having it for a very good reason. So with that, let's go ahead and draw this out. Let's zoom in with our simple third-class lever. Let's go ahead and add the fulcrum on the left like they have it. And you can see they got the fulcrum right here. And they've got FE pulling up here. And then they got FR pulling down here. So let's go ahead and do that. So we got an FE pulling up right here. And we got an FR pulling down right here. And let's say our FR, let's say we know that is 10 pounds. That's what our load is, this little ball that we're trying to lift up. It's 10 pounds. And let's say we're trying to figure out how much effort force our bicep needs to pull to lift up that force resistance. And then we look and we say, okay, let's say that the insertion of our bicep into our forearm is 2 inches. So in other words, the distance from our fulcrum or our elbow to our effort force or our bicep insert is 2 inches. And let's say the length of this forearm is, let's say it's 10 inches, just to keep it nice and simple. At least at first glance, it'll look simple. All right. And then, of course, let's go ahead and ask our 2 questions again. What is our mechanical advantage? And, well, what is our force effort in this case? So how much will our bicep have to pull? How much force will the bicep have to pull with to lift up that ball? And so first things first, we need to solve for mechanical advantage, and we need to know which equation we're going to use. Well, if you look, we have both distances. So then we're clearly going to use our Ima equation. So let me go ahead and just copy this and paste it right here. And we'll set this equal to that. And of course, we'll plug in our numbers. We know our DE and our DR. Well, we know there's 2 distances. I guess we haven't really labeled. Now, at first glance, you might think that 10 goes on top and 2 goes on bottom, because that's the way it's always been, is the big number goes on top. But that's what makes third-class levers special. If you look, the DR is by definition the distance to our FR. So that makes this our DR, which means it's our bottom number, 10 inches. And that makes this our DE because it's our distance from our fulcrum to our effort, which is 2 inches on top. And if we plug this into our calculator, we do not get 5. So we clear this out and we say, what was it, 2 divided by 10, we get 0.2. So we get 0.2 for our mechanical advantage because inches cancel out. And you might say, well, that's a little weird to have a mechanical advantage of less than 1. We haven't seen that yet, but there's actually a very specific reason why. And we'll talk about that in the near future.
But from there, we're looking for our force effort, and to do that, we need to assume an ideal effort force. So we need to go ahead and plug in our ideal effort force equation. So let's drop that in.
And then we know what most of these numbers are. We already know what DE over DER is, well, let me get my pencil out. It's, what, 2 inches divided by 10 inches. And then, of course, we know FR as well. We know that's 10 pounds. And so the question is, what is FE? Well, to get that, we will just simply cross multiply and divide. So we do what? 10 times 10, which is 100. 10 times 10, which is 100, divided by 2. So 100 divided by 2, and we get 50. And then, of course, inches cancel out, and we're left with 50 pounds. And so FE equals 50 pounds. And you might say, well, wait a second, Mr. Anderson, that's not much of an advantage. That's my force effort is 5 times bigger than my force resistance. That seems like a huge disadvantage for my force. In fact, obviously is a huge disadvantage for our force. And that is true. And so I want to drive this home. Mechanical advantage doesn't make your job easier. It just gives you a certain advantage. And every single equation we've looked at up until this point, our distance was always the disadvantage and the force was always the advantage. But in this case, our distance is our advantage. So what does that mean? Well, how can our distance be our advantage? So what's going on here? Well, if you look, I'm applying my effort here. So I'm trying to lift this forearm up a certain distance. And to do that, what we need to do to lift this bar here straight up. So let's go ahead and look at our bigger example here. If I wanted to, well, let me pick a better color. If I wanted to lift this bar up, well, my force resistance is going to go much farther than my force effort to get this sort of rigid bar moving up.
And so the effort force doesn't have to go anywhere near as far as the weight will actually go in this system.
So even though it's applying more force, it's getting the same job done.
Which means the work is equal. But think about that. If the force is bigger, the only way that can happen is if the distance is smaller. So basically what we're saying is to decrease the distance, we have to increase the force.
So the bicep might only contract 1 inch. It might only pull up 1 inch. But because it does, the load is able to lift up 5 times farther, which is 5 inches. And in fact, that's how mechanical advantage of a third class lever always works. And that's what, when mechanical advantage is less than 1,
That's what that means, is that you have a distance advantage instead of a force advantage.